we're going to do problem 2 in this exam, which is don't get entangled by this problem. So you can imagine the plots that we're going to be looking with, which is going to be log of viscosity versus log molecular weight. Molecular weight. You're going to see two different regimes. So 3.4 is reptation. Rouse, which is going to be 1, that slope. Critical molecular entanglement weight. So remember, ME is going to scale proportionally to TG, or the stiffness of your backbone. And what else? Let's look at log of diffusivity versus log of molecular weight. And we're going to see two different slopes. So two different regimes. So we're going to look at here, we're at -1, then -2. Yep, so let's go ahead and actually derive those out, and let's see what the problem's actually asking us to do. So I am looking at the diffusive behaviors of polymers A and B in pure melts of A and B as a function of molecular weight. So let's remind ourselves, again, you might want to print this out and have these polymers kind of cut out. So A and B. So B has a larger TG than A, so we're going to expect to see some shifts there. So let's go ahead and look back. So A and B are the polymers that we're looking in. So again, if I have to plot, let's see, a plot of log of viscosity versus log of molecular weight. This is my A. And here, so this is A, and B is again have F here. So if I'm looking at this polymer, so I should expect that, oops, and then that actually, well, let's just put it here. Again, same slope, but again, just kind of, that occurs at a smaller, again, more flexible, easier to entangle. So that's just kind of a graph of what you might expect them to see. All right, so now we want to ask or see what the problem's actually asking us. So A has a molecular weight of 10 to the 8th grams per mole. B has a molecular mass of this. I have a monomer friction factor of this, and we're at room temperature. So let's go ahead and start to define some values. So K equals 1.38 times 10 to the minus 23. My T equals 300. Beta equals 1 times 10 to the minus 13. I did that already just to kind of get us in kilograms. And then finally, my repeat unit, my molar mass repeat unit of A is going to be equal to 24 plus 4, and my molecular repeat unit of B is going to be 24 plus 2 times those fluorines, 19, and that's going to be my values here. I know that my molar mass of A is going to be 10 to the 8th, and then my molar mass of B is going to be equal to 500. So I need to figure out also my Na is going to be equal to my molar mass of A divided by MRA here. Let's look at that. Don't worry about those kind of values there. What about my B? So MB is going to be equal to MMB over MRB right here. So that's my, again, the number of, my repeat units, again, my degree of polymerization. So let's go ahead and then see what this question is actually asking us. So we need to calculate the diffusivity, D, and longest relaxation time of each melt. And do these values make sense qualitatively? Approximate C infinity based on the polymer backbone structure. Which is more likely to behave mechanically as a solid or liquid? What would the Deborah number be for each melt? So let's go ahead and start to kind of think about this problem. So if I want to calculate the diffusivity, I know that for my polymer A, again, typically my molecular entanglement weight, my ME, or my Epsom C, about 10 to the 4. So clearly, A, I'm in reptation, and B, I'm in my Rouse. So if I want to calculate the diffusivity of B, so let's focus on B for a little bit, I know that my Rouse diffusion is just going to be D Rouse. B is going to be equal to KT over eta times my number of b. So I can calculate that out. So d rouse b will be equal to k times t divided by my eta times nb. And that's going to give me my diffusivity again, meter squared per second. Excellent. So I've got that value down. I can also calculate the longest relaxation time. So we know the longest relaxation time is going to be T Rouse is just going to be equal to my Rg squared over my diffusivity here. Diffusivity of my Rouse. So, and then remember, we are in the melt state, so that means we're in an ideal solvent. This is equal to R squared, the 1/2 over, or actually R squared, not the 1/2, but just this to the 6th, which is going to be equal to C infinity N L squared over 6. So when I do that, I could figure out, and I could see actually, I need to calculate or estimate C infinity. Now we know that C infinity is kind of, again, the stiffness and the kind of the ease of rotation around your backbone and kind of these different kind of bond angles. So if we look at the polymer here, I need to kind of, or we'll see that here, I'm going to have these flooring groups. These flooring groups are going to be much more difficult to rotate around. So again, C infinity kind of scales with your TG. So that is going to kind of be a larger value here. So again, you're just asked to estimate it, but we know that C infinity of B is going to be greater than C infinity of A. So the other question we have is we actually see it right here, what is our L? What is our bonding, our monomer, that kind of repeat unit, my monomer length? Well, remember, we could approximate that as just kind of our carbon-carbon saturated bond length. So L is for this problem, since we know both of those bonds are 1.54 times 10 minus 10. So 1.54 angstroms. So let's go ahead and solve and finish out this problem. So L equals 1.54 times 10 minus 10. I'm going to say that C inf B is going to be equal to, I'm going to say that it's equal to 10, while my C inf A is going to be equal to 6.9. That's actually what it is for polystyrene. So I'm going to, I did that kind of research a little bit ahead of time. So if I want to look at my TB, my tau B in the Rouse regime, it's just going to be equal to, again, C inf B times NB times L squared divided by 6. But this also is going to be times D Rouse B. And when I do that, I get a very, 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 very small relaxation time. Again, this is relaxation in seconds, because look at the units here. So we know this is a meter squared per second. This is in meters squared. This is unitless. This is unitless. So the seconds go up. Again, very, very, again, very, very small polymer. You get only 7 repeat units, or really little oligomer. So very small relaxation time. Makes sense. Now, what about A? Well, A, we know that we are in the reptation regime. So we remember that to kind of calculate our tau reptation, we need to kind of think about the scenario, our general equation for diffusion. So x squared equals d times t, or again, if we want to calculate our longest relaxation time, tau reptation, that is going to be equivalent to when, actually, let's erase that right here. When we kind of move a distance or we create a new tube, i.e. where x equals L, where L is equal to our contour length in L. So when we move a distance L squared, and that's going to be equal to inside the tube, or we want to create a new tube, move a whole contour length. So inside of our tube, we are looking at basically diffusion in the tube, which is diffusion in the Rouse regime. So d tube equals d Rouse, which is going to be equal to kt, since we're dealing with A and A right here. So the number of A repeat units. So that is going to be our expression for our d Rouse or d tube. So our tau reptation is just going to be equal to n squared L squared over d tube. So let's go ahead and calculate that out. So again, makes sense. Meter squared, meter squared per second. So seconds. So let's look and calculate. So d tube, which is going to be equal to k times t divided by beta times Na here. So, and then I will look at tau rep, which is going to be equal to Na squared times L squared divided by D tube. And you see a very, very, very long relaxation time, 10 to the 7th. Again, so you can see kind of, again, why these are basically permanent crosslinks. It's going to take to the 10 to the 7th seconds. Because again, look back at that's a lot of repeat units. That's a huge, 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 gigantic polymer. So that's going to take a long time to disentangle from itself. So that's our tau reptation, and we know that the way that we can get our diffusion is by knowing the relationship that our basically our longest relaxation time is going to be related to when our polymer moves base generation squared over basically your D, your diffusivity. So my D of rep is just going to be equal to, again, this, I'm going to switch around. So I'm going to look at my Rg squared, which I know is NL over 6 times L squared C infinity. And so that is going to give me that over my tau rep. So again, let's look at the units. So meter squared, seconds, everything looks okay. I have, so my D rep is going to be equal to my C inf A times Na times L squared. All of that divided by 6 times tau rep. And you can see a very, 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 very small diffusivity, as you might expect in the reptation regime. But these are kind of exaggerated numbers, extreme examples. That's it. So, which is based on the background structure. So, which is likely to behave like a solid or liquid? So, clearly we remember that our Deborah number, so D is equivalent to our relaxation time over experimental times. So, when our DE was much, much, much greater than 1, again, this told us that we were going to be behaving like a solid. So when our DE, again, think about this. DE is much, much greater than 1, so our relaxation time is much, much longer than our experimental time scales. If our DE is much, much, much less than 1, then we're looking at a very, very small relaxation time corresponding to our, or relative to our experimental times. So that's going to behave like liquid. So we still can't answer this unless we know what those experimental timescales T are, but generally speaking, looking at these relaxation times, I'm pretty sure this is going to behave like a solid, and I'm pretty sure that this is going to behave like a liquid. So, as you might expect. All right. So, again, we can't answer that question. We can't calculate Deborah number unless we actually know the experimental timescales. So, for what melt are entanglements transient, which are permanent? Again, we say that already. So if the polymer, A is going to be in our Rouse regime, so those are permanent entanglements. B, we are in the A is in the reptation regime, so those are permanent entanglements. B, we are in the Rouse regime, so those are transient entanglements. If two polymer melts were both in the Rouse regime, same molecular weight, which would have the longer relaxation time? Explain your answer. All right, so if we had these two polymers were both in the Rouse regime, so we know that our diffusion of the Rouse, so if we had the same molecular weight, and let's just say, for argument's sake, that Na and Nb were equal, equals Nb. So if we were in the Rouse regime, what would have the longer relaxation time? Right here. Well, we know that the T Rouse is going to be related to our D Rouse here over this Rg squared. And we know that the Rg squared, if we have the same molecular weight, and actually this is kind of a little typo there, it shouldn't be the same molecular weight. Basically, they have the same degree of polymerization, because that'll change your answer a little bit. But let's say, for example, they have the same degree of polymerization, but everything else here is the same. L is the same, everything. The only thing that's going to change is C infinity. So when we look at our polymers, the long relaxation time will be, again, polymer B, because of that those fluorine groups. So, and then that's that answer. And then finally, which polymer will have a larger size, thickness tube in the reptation regime? So remember, that tube kind of tells us like the number of entanglements, right? The free volume that it can access. So the size of the tube really depends. It's kind of saying, okay, there's like entanglements all over here. It's where the polymer can kind of move around. So if I have a more flexible polymer, there's more likely to be entanglements, and so I'd expect my tube to be a little bit smaller. Whereas if I had a rigid polymer, again, more rigid polymer, less entanglements, I'd have a little bit larger tube. So I'd expect that B would have a larger tube. But again, that's a kind of more complex answer. You want to elaborate on that, and I'd be interested to see kind of your arguments for that. All right. So I had my undergraduates create a plot of log of viscosity versus log molecular weight for the pure melts of A, B, C, and D. Do you agree with their assessment or not? Explain. So let's go ahead and look at this plot. So let's look at this page here. So A, B, so looks like from this plot, they're saying that, remember, we know that this is our critical molecular weight entanglement. So this is saying that my TG of D is less than my, again, highest TG, again, just like this idea, that example of polystyrene versus polyethylene, more flexible, easier to kind of entangle. So my TG of D is going to be less than my TG, what's the next one here? Blue, that's going to be C, less than my TG of A is less than my TG of B. But we know from our, again, this is why this first part of the problem is so useful, and you want to kind of look at these rankings. I know that my TG of C, it goes 1, 2, TG of C is greater than D, is greater than B, is greater than A. So TG, let's go back over here to this problem. Oops. I know that my TG of C is greater than my TG of, let's go ahead and look back. TG of C is greater than my TG of D, which is greater than my TG of B. It's greater than D, it's greater than TG B, it's greater than TG of A. So it should be here, this should be C, D, B, A. That's it. And we know that the slopes is going to be 1, 3.4 in those regimes. That's not going to change. Just this kind of shift in molecular weight. And again, don't worry about kind of if these are offset at all. They don't mean really anything. It's just for visualization purposes. All right. So let's go back to this question. All right. So I don't agree, and we just explained. So they should scale there. That's why that first problem is so important. Cut it out, print it out, draw it, and keep that kind of table with you as you answer these problems. So let's see. Draw the log of diffusion versus molecular weight for the mixed melts of AB, BC, CA, and CB. Don't worry about the placements of each of the molecular entanglement weights, but label the value of the slopes in each of the regimes as well as the different regimes. All right, so let's go ahead and think about, so we need AB, BC, CA, CB. So let's go ahead and write those down. AB, and then I'm looking at, so we know that chi AB was equal to 5 times 10 to the minus 3. I knew here, AC, that chi AC is equal to 1 times 10 minus 4, and then chi of CB was equal to chi of 8 of CB, is equal to 8 times 10 to the minus 5, and then finally D was equal to chi D is equal to minus 1. So let's make sure that they were asking for that again in the previous problem. So let's read back through it. So AB, we've got AC or CA, we've got BC, we've got that right there, and then, there's a typo here. This should be, instead of CB, this should be BD. That was a typo in the exam. I knew something was was kind of off. So that was a typo in that exam that we caught during our exam. So let's go ahead and look at this problem. So we actually, one of the questions actually that this should be kind of elaborated is, we're looking at these kind of mixed melts, correct? So one thing, don't worry about the placement of the entanglement molecular weights, but we need to label the value of each of the slopes as well and the different regimes. Well, one of the things that we need to kind of look at and understand is that we know when our chi n is greater than 2, we will not mix. So the diffusion will drop, the inner diffusion will drop to essentially 0. So that's one thing that we need to be on the lookout for. But these are pretty small, again, small values. It's going to take quite a large polymer in order to kind of get that to be beyond 2. So let's look, for example, let's look at chi-AB. So let's solve for 5 times 10. So solve for 5 times 10 to the minus 3. Solve when this is equal to times x. When is this equal to? So 400, again, seems pretty large, but remember, at 200, you're already past the number of units for polystyrene in order to kind of entangle. So again, you're looking at fairly large kind of polymer chains there. But that's kind of one caveat that you could kind of answer in this question. But let's look at this more generally. So in the problem, it says that we don't have to worry about kind of the placement of entanglement molecular weights, but we need to kind of look at the slopes. So we need to kind of understand here that the big idea is that we get this boost. Our diffusivity increases by an order of n when our chi value is less than 0. So that only occurs for VD. So all the usual suspects, so everything is going to be the same, but the exception is going to be that our, let me kind of show this. So all the curves are going to basically look like this. Oh, excuse me. That's the opposite one. All the curves are going to look like this and this, but one of the curves, BD specifically, is going to look flat. Oops, here, you're going to see kind of this flat, and then again, the slope -1, the slope 0. You're going to get this boost in diffusion due to that kind of parameter here. So again, as long as we don't cross this value here, then we know that there's going to be some interdiffusion and kind of some value there. But once we kind of reach or go past this critical threshold, we know that diffusion is going to drop to 0. Excellent. So that's pretty much it for this problem. So we'll go over that in our exam review session. I hope this helped. And yeah, hopefully now you're experts on entanglement. I'll see you in the next video. Thanks. Bye.